So it is a huge pleasure for me to introduce my friend Eike Schling. Eike studied architecture at the Technical University of Munich and then worked a few years in London in an architectural practice and then went back to academia to Professor Barthel's structural design at the Technical University of Munich. And then he contacted me, maybe in his earlier years at this place, because he knew that I'm giving some guest lectures on geometry, and he went there, and amazingly he understood something. So this was really for me a big surprise, and he has great geometry intuition, I call it, right? Even if you don't have a big mathematical background, you can have a great geometry intuition, and you can invent concepts which are interesting to geometers. And this guy is Eike Schling. So he continues to surprise me with very nice ideas which bring up challenging problems which we are not able to solve right away, where we really have to think about, and some interesting mathematical theories even come out. So I don't want to steal more of his time because the time is short anyway, so please, Eike, move forward. And
Thank
we have
you.
a difficult slot after lunch, but I know you're a great speaker.
That's
so
fine.
You will do fine.
Thank you. I have to be honest, Helmut, when I started my PhD and I thought I need mathematicians to help me, I actually contacted the TU Munich first. I didn't even dare to write to you. You were much too high. Are you even listening, Helmut? He's not. He's not listening to me. I'm talking to you, Helmut. When I first did my PhD and I needed mathematicians to help me, I actually didn't dare to write you an email. I wrote to the TU Munich. I wrote to the no, because you were much too I don't know, high that I didn't dare to write you. And I wrote to the Technical University of Munich, and they said, "We don't know, ask Helmut Pottmann," and you were actually at our school that semester. Yeah, that's how it happened. Okay, you forgot to mention the final thing, and that is I'm at the University of Hong Kong right now, but I will actually move to Hannover in a few months' time, and we're now setting up a team for the structural design chair there. So please listen carefully, and if you like my presentation, write me an email. Yes. So thank you it's really an honor. I've been coming to the GCD, I think since it began, right? And now to be standing up here and present to you is really a great honor for you. I'm actually a little nervous, which I'm normally not anymore. And I looked back and looked at when is the first time I actually came to Vienna, and I was invited here in 2016 this was, I think, I must have just met Professor Pottmann back then, and I was invited to present some of my classes that I was teaching at the Technical University. And I want to start with these very simple examples because for me as an architect, those were the tool of how to learn about geometry, and a lot of the things I did back then, that's now 7 years ago, more than 7 years, actually has very much to do with what I'm still doing today. So after I came back from London, I wanted to investigate with the students how to build complex grid shells or surface structures, but how to do that with very simple means, with using always the same elements and the same parts. And I thought the good thing about this quest is if all the parts are the same, then they're really easy to produce. So I can just ask students to produce a part, right? They can make up any part they want, and then just start adding it together and see what happens, right? And so students did that, and then shape emerged from this, right? And I thought it was really interesting. Another student, for example, decided a different thing. They decided he wanted to use cubes, right, to create a three-dimensional doubly curved surface like this. And I said, no, that's not what I wanted. I wanted you to design a complex object that then emerges into a 3D geometry. You can't just use cubes. Cubes want to be in a flat surface. He did it anyway, and then the rest of the semester we struggled with the idea of the gap, the void between these cubes, right? And first we thought, okay, we can just make single rings that are different in size, but we realized they're not only different in size, depending on the angle, they also start shifting, right? Because they actually are not all in the same row. They have a curvature sideways, and there's also a twist that we have to accommodate for. It was getting really complicated. But again, we didn't know it, but we were learning all the time. And we also realized that this is a continuous law and relationship. So these are the rings on the top and the bottom, and they actually match up nicely into a continuous pattern, creating this beautiful sculpture. One more example that I thought was always quite nice, we had students looking at folding and curved folding. It's really a hip project nowadays. So they were really doing this very fundamentally. What if I make a curved crease? I get a convex and a concave, and I can mix and match that, right? So I can create convex on the outside, concave on the inside, or vice versa. And so doing this, I can also create modules where I can control the tangency on the outside of these modules. And they wanted to build a three-dimensional surface with this, and it was getting, we tried not to use the computer. So we tried to do only repetitive parts. So we had this idea, why don't we just look back into the Schläfli diagrams of Platonic solids. So if you look at the Platonic solids, you can describe the whole geometry just with two numbers. 4, 3, for example, is a cube. 4 means 4 edges to each side, and 3 means 3 faces are meeting at each node. Right? So these two numbers describe the whole geometry of a cube. So if you take those and you think about it long enough, and you want to create a curved crease model out of it, you have to, if you want to flatten that curved crease model flat on the ground, then the pattern has to look like this. If 3 things meet, it has to be 120 degrees that they meet with at. And every side has to be 4 sides. So I can continue one of those elements and add 4 sides. So 1, 2, 3, and 2/2 is 4. So this must be the flattened version of my module, just based on the rule of a Schläfli diagram. So if I then put circles inside that and I fold it, voila, it actually works. We didn't believe it ourselves, but you can just do that with a crayon on an A4 sheet of paper, and you can create these beautiful curved crease Platonic solids as cube or tetrahedron or octahedron or dodecahedron or icosahedron. And so this is the one that the students decided in the end to build. And we learned a lot about geometry, about how these things go together, and how if you understand geometry and you understand the construction, or you want to simplify the construction, and you combine that even with structural knowledge, you can create very meaningful design of what I call repetitive structures, so structures that always use the same elements. And this became my PhD, and at this point still Herr Pottmann became my PhD advisor. And in this work I looked at a lot of structures that are built today out there, and I really tried to understand how can I capture this idea of repetition better. And in the end, I had to start learning more about geometry, and I realized that there's always joints, edges, and faces that need to be solved, right? So before I get into the detail, I want to pick one of these examples out for you, and this is the one in the middle. This is the Centre Pompidou in Metz. I was quite intrigued by that because it had a smooth network that constructed these things, and all of these elements had to be produced for that specific curvature. So we're talking about very complex edges, and I think design to production helped, and worked together with Holzbau Ammann, a partner that we're working with today. That's why I'm picking this. And so you can find these images of how every single edge had to be glue laminated into the right curvature and twist, and then 3D milled to the perfect shape, and then brought to site in these all bespoke elements, right? And so I learned about the complexity of curvature of these lines. So now let's go back. I tried to tackle these things in my PhD, and I realized that when we build something as an architect, we can either do it discretely, so using straight elements, but then we have all the complexity in the node, or we can do it smoothly, and then we have very simple joints, but then we have all the complexity in the edge, as we've just seen. And I was more interested in the smooth option, but in general, I just wanted to understand how we can control these parameters. And so I need to pick one specific thing out that really governs a lot of my research, since it's understanding the curvature at play here, right? So if you follow such a smooth line on a surface, it actually curves in 3 directions, right? It curves up and down, and that's what's the normal curvature, that's the normal thing we measure, but it also curves left and right, that's the geodesic curvature. And if you walk along that line, you might also tilt from one side to the other, and that's the geodesic torsion. For engineers, this is very easy to understand because those 3 local axes of a beam are the 3 bending axes, and in geometry, those are the curvature axes. And so this is really, once you understand that, it's quite simple. And so I try to have a table of parameters that I need to control in any grid shell in order to create repetitive parts. And so I thought, if I just list all the parameters and they're all the same or constant throughout the structure, then the elements also have to be the same. That's an easy thing to do. So I started listing them. There's the element length, and the intersection angle. And then for these smooth networks, there are these 3 curvatures. And you can actually just transpose that into the discrete case, and then instead of 3 curvatures, you get 3 node angles. These are interchangeable, actually. You can calculate from one to the other. And that gives you a total of 8 parameters. And there are, of course, more parameters describing the faces, but I won't talk too much about those today. So I thought, okay, that's it. But then I realized, as an architect, there's actually more, right? So you can actually build a structure from repetitive parts that's geometrically not repetitive. So there are some tricks we can use as architects and people who manufacture this building. And those tricks are the tolerance you use in buildings to account for changes in length, the hinges, joints we use to account for the change in angle, and deformation to account for the change in curvature. And these 3 criteria nicely actually map with these different parameters, right? So curvature parameters are dealt, you can deal with elastic deformation, hinges, you can deal with the angles, and so on. So this was the very simple theoretical framework I started with, and then I started analyzing existing buildings to see how have architects solved this problem in the past. We've done a lot of work on this, and I don't have time to show a lot, but I always have to show this one example because it's one of the most important precedents to my research that came afterwards, the Multilateral in Mannheim. So we all know by Frei Otto how he designed this grid shell by hanging a net and then creating this net by bending these wooden laths into the correct shape. And so we remodeled it, and we used these parameters to measure all the different parameters in this net, and here you go. There are no complex angles other than the intersection angle, and there's a lot of different curvature. And if you look at how it was built, you can see Frei Otto used a hinged joint to account for the different angles. He used a little tolerance in the length to account for that, and he of course bent all these lamellas. So that's quite simple. But the good thing about this is now that we could really measure these parameters, and we could measure each axis, we can actually learn more about the structure and how it was built, because we can transpose the curvature into the actual bending stress that then occurred during construction. So we can take these values and we can use the Euler-Bernoulli theory to calculate the bending, and we can use the Saint-Venant theory to calculate the shear stress for torsion. And actually for very high twisting, we need to also account for additional normal stresses due to this helix effect. So that's called the helix torsion theory. We can use that too to calculate all the stresses occurring through this geometry. So just by doing a simple geometric analysis of that final geometry, we can actually simulate what the stresses were when this Multihalle Mannheim was first built. And they did these tests too back then. I don't want to say this is brand new, but back then they only tested for the spatial curvature. And so this is now dissecting all the 3 axes of the profile and also seeing the twist that happened. As I said, we're using this a lot to analyze buildings, and I just want to highlight one more publication we did, which I actually never presented. We looked at Vladimir Zhukov, early pioneer of steel structures from Russia at the turn of the 19th century. He really revolutionized the way of how to build with steel, and the mindset was very similar. How can you take the simplest elements, always the same elements, combine them and twist them a little bit elastically or maybe even plastically? I think Zhukov didn't care, but how can you just tweak the rest on the construction site to create great doubly curved structures from very simple elements? And we could actually remodel those and find out, for example, that the non-constant torsion is actually highest in the top element of this tower and must have caused a lot of pain to the workers because we knew the L profiles they used, and we could realize that it was almost 40 kilo over a meter lever that they had to pull to twist this into the right shape. And we could also model some of the other grid shells and actually learn about the construction process and also about the geometry that Zhukov must have used. If you're interested, and I still have minutes, I'm going to show you more slides, but I deleted them now because I want to show you my innovation. But it is really a tool to learn about what must have happened in the past, because these curvatures were real and they needed to twist elements on site. So I used this to look at all these projects and to come up with strategies for discrete, hybrid, and smooth networks and how they could be made repetitive. And it was getting a little nerdy at this point. So what's much more interesting is how we can use this knowledge to design new buildings, new networks. And so I had this idea, if I only look at smooth networks, I could actually list all the possible combinations, right? So if I say, for example, all the curvatures are the same, the lengths are all the same, and the intersection angle are all constant, what's the result, right? And then I can only change one variable is changeable, x means changeable. And what if 2 are variable and 3 and 4 and so on? And then you get 33 solutions. These are all the possible solutions there are, right? So then you can start filling that in like a periodic table of elements. You know these are all the slots. So let's just start filling them in. And some of them I think just don't make sense, and others maybe we haven't found yet. But when I did, I of course immediately recognized some of them, right? So you have the cylinder, you have the geodesic dome that we just built before. Here that's Multihalle Mannheim right there, the Chebyshev net. So there are some familiar faces popping up on this scala, and there's other ones that we hadn't seen so much yet, and that were really interesting to investigate. I specifically focused on this one, and that is asymptotic curves on minimal surfaces. Why was this so interesting to me? Again, it goes back to these 3 curvatures that I described before. If you keep one of them constant, they harmonize, or they create these 3 different networks. So if you have a constant geodesic curvature of 0, you get a geodesic network on the top. If you have constant 0 torsion, you get a principal curvature network. And if you have constant 0 normal curvature, you get this asymptotic network right here. And why was I so interested in it? Because you can create doubly curved surfaces only on negatively curved surfaces, but you can create these doubly curved networks with lamellas that are initially straight and they're standing upright, so they can actually take local bending, but as a global structure, they can work as a grid shell and transmit forces like that. And I realized only then, or I think much later, that this is very similar to one of the first model I built. This probably, if you look at it, must be following the same geometric rules. So we looked into that, and we went a step further and designed these asymptotic networks on minimal surfaces, because in that case, they meet precisely at 90 degrees. So in a minimal surface, the two principal curvatures are exactly the same, they're at equilibrium, and so the axes where there's no normal curvature are also at equilibrium, exactly 90 degrees from each other. So you can create these beautiful models out of straight strips where every joint is identical and they all meet up at 90 degrees. This first model was built on a Schwarz D surface, so we just used a mathematical model, but soon enough we developed our own little script to trace these paths, and so we started designing minimal surfaces, and then clicking on these minimal surfaces one by one. It took very long to trace these elements and try to get familiar with the grids we could create, and you see some singularities popping up at planar areas. So we cannot control this as a designer. This is just an emerging net based on the surface we're doing. Actually, since the surface is also predefined as minimal, the only thing we can design at this point is the boundary. But we were quite intrigued by this, and so we started building our first prototype in timber, and you see we learned from Frei Otto. So for example, we started adding several lamellas together on the sideways to get more stiffness, to prevent buckling. The first model we built purely in space, and it was very hard to control this. It took us forever until we noticed in our second prototype that, just like Frei Otto, you could just assemble this flat on the ground. You can see that in the row down here. If you assemble these lamellas flat on the ground and you just push on one side, the whole network will naturally deform into the design shape. It is actually a compliant mechanism. We noticed this purely by chance, but because there is a scissor joint which kind of restrains the movement, and because you have a high profile which can only bend sideways and twist, there's not that many ways to go for this network. So based on this, and I have 23 minutes to talk, perfect timing, so I have 20 more minutes to talk to you, I would like to show you 3 projects, or actually a few more, but projects in steel, glass fiber, and timber, in which we use this technology of asymptotic grid shells to design these structures. So the first one was part of my PhD at the Technical University in Munich. And the workflow went exactly like I explained. We only designed the boundary. It was this beautiful courtyard, and there was a tree in the middle. So we designed this catenoid surface around it and then deformed it to create a minimal surface. We actually did a mesh optimization back then. And then we used the algorithm to trace these paths one by hand, because we didn't have Helmut yet to help us. And then we got this orthogonal network, and in the end we just had to add some edge support and supports and diagonal bracing to make it into a real grid shell. So what we get is a very complex structure that can be built from just flat sheets of metal, straight metal, and has repetitive joints at 90 degrees. And the whole pavilion was then, or the whole steelwork was delivered to site and looks like this. I asked 3 times if it's really everything, and they said yes, it's everything you ordered, because it can be packed so nicely. It's flat. So the workflow to build this is we take these straight lamellas and we prefabricate these 90-degree joints one by hand. Everything is really low-tech at this point. We slot it together into planar segments, and these are then deformed into the 3-dimensional design shape. We need to fix that design shape by just fixing the 90-degree joints and adding some extra edge supports, and then everything is brought to site and assembled like a 3D puzzle into this grid shell. And finally, we have to add a pre-tensed cable network to ensure that it's nicely braced. And this is the steel pavilion. This is now at the TU Munich, and it's become kind of the Instagram background. Yeah, everybody, it's so Instagrammable. So if you want to have a picture, go there. Yeah. All right. This was quite successful, and we had people saw this and actually asked us. So we got our first commission for a small roof, which was now we had a client. It had to be structurally approved outside the university. It needed to be on budget and on time. So very different situation, but we were quite happy with this, and we went for a modular prefabricated approach. In this design, everything is bent. So the grid is elastically bent, the arch is being bent to stretch the membrane, and even the cantilever beams are plastically bent to fit to the grid inside them. So it's a really nice building process, because we actually do kind of what Frei Otto did. We do the inverted hanging shape, we pull it up, and it naturally goes into the design shape. And then once we have that final shape emerging, we just welded the joints at that particular situation. This is not a minimal surface, so the joints in this case are not 90 degrees, they just end up where they need to end up. And so the module looks like this, and 4 of those were produced and then brought to site. These are my 3 kids on the site visit with me, and this is the final project. So what we got really intrigued by at this point was this this kinetic behavior of these structures. So there was this beautiful inherent logic that these grids would move in a very specific way, and they would also find an equilibrium state, which was not necessarily flat. So the interior stresses would push it to stay maybe sometimes in a 3-dimensional state. And we started investigating different topologies, right? So first one flat topology with singularity, cylindrical topologies. This one is 4 cylinders with 4 singularities. And we were just interested in what's possible, what movement can we achieve, and how can we control this movement? So then we started to think about actuation. Can we include cables and then have this transformable roofs appear that we can control remotely? Maybe this could be, roofs that open up and close during the day and at night. And we investigated 7 of these shapes and also learned a lot about the influence of, for example, cylindrical topology, or for singularities inside the net, and how they restrict the movement, or how the movement is broader and more open. And we had an interactive exhibition in Hong Kong to actually have people, play with this themselves. We built these glass fiber models where you could just learn about this movement yourself. And we created a digital workflow in which we could simulate that movement and then measure the curvature of each state and calculate the total curvature in each particular state. So we have the total curvature, geodesic curvature here on the right. On the top is the torsion. So when it's flat, the total torsion is 0. There is no torsion, right? But there's a high total geodesic curvature. Now, if it's in 3D, it actually has much less geodesic curvature, but a lot of torsion. So there are 2 kinds of curvature going against each other. And so depending on which profile you design, you can now design where the equilibrium state will be, where this grid will naturally stay, right? So if you make it very much resistant to torsion, it will try to avoid this state and go towards the flat state. If you make it very resistant to sideways bending, then it will pop into this state. And so that's what these lamellas will do. They don't like to be, they like to be twisted, but they don't like to be bent. So basically we have now a 4-dimensional or 5-dimensional design, right? We can design the shape. we can design the movement, and we can design where that movement in the energy state ends up with by designing the section. It's getting very complicated, but it's also really cool that you have these natural movements that are very strong, by the way. So each state is very strong in itself. It doesn't want to leave that family of surfaces. And so we designed this umbrella shape that in theory should naturally close just by its internal stress states. That worked really well at a 1 to 10 scale. We then scaled it up to 1 to 3, and it already kind of went like this, right? And then at 1 to 1, gravity plays its role, and it just wants to fall open. So everything I just said works if you don't account for gravity. If you do, it doesn't work anymore. But for us, that was actually not too bad, because what we could do, we could have a tensile ring that would force it closed, and then if we wanted it to open, we just have the ring open, and the flower would naturally start blooming. So this is what we did. Actually, I was stuck in Hong Kong at this point, so all credit goes to Jonas Shikore, who now just finished his PhD on compliant grids with this as his project. And it's really a different kind of game there. It's really high tech. If you want to have these movable structures, we needed specific hinges that would account for that movement with no friction. And we have this actuator in the middle that controls the movement. Here are some moving pictures to show how this works. This is always done as a student project, so we have students preparing these templates and preparing the lamellas, and everything is done from repetitive parts. In this case, it's even a rotational surface, so all the lamellas are the same, all the joints are the same. It was prefabricated in the shop into the cylindrical network, and right outside the factory, we built the concrete and steel foundations, and then the whole thing was lifted in place. Finally, we added a shading facade, and this is actually now a next research project that's going on. How can we clad these transformable nets with a membrane that works? So this is a final shot, and you can see the actuation cable leading up. Right, in the meantime, while we were looking at these transformable structures, we got a lot of criticism for being only in the sculptural realm, right? So we wanted to make this into a building product. So the questions were, how can we clad this to have a facade? How can we have these lamellas be resistant to buckling? And how can this whole thing be a little more sustainable? We started with the facade investigation, and I just met Marias. She had played a big role. I don't think I have an image of you here, but you did your whole master thesis on square glass tiling of asymptotic networks, and we came up with the idea of actually tiling it or having developable panels on this facade. And so the question is, how can we have a third direction that's also straight and simple and flat? So these mullions, these facade mullions. And so our idea was that we just add a family of geodesic planks. So we use the same material again, this time flat in a triangulated direction. We wanted to build timber grid shells from this, so use timber and reuse the timber, so everything should just be combined. We have off-the-shelf planks directly from the sawmill that we can use and then only screw together, like weave them into this basket. And I'm showing this slide, and I'm showing you the Centre Pompidou in Metz again, because by shifting these lamellas a little bit, we actually get this tri-hex pattern, the same pattern that Shigeru Ban used, and suddenly the circle started closing because we're working actually with Holzbau Ammann again. The same group that built the Centre Pompidou in Metz is now helping us to realize this project. So this one is not trivial, though. It's very hard to generate a mesh. And so to generate these combined meshes of asymptotic and geodesic planks, we worked with Helmut. By now we were with our first names. And this group in Kaust. And Hui Wang actually did the discrete optimization for these. So there's several things you can do. You can have one asymptotic and two geodesics, or AGs, or also families of 4. We are focusing on 2 asymptotics and 1 geodesic, the one in the middle. We call it an AAG network. And you can discretize that by having several rules on a mesh. For example, you can ask all neighboring points to be in the same plane as the single vertex, and that will give you an asymptotic mesh. And you can ask for diagonal points to be in one plane with the surface normal, and that will give you an additional geodesic net. And we could create these networks and create these AAG meshes. And what we realized, to initiate this optimization, we usually had to start over with a rotational surface. So for our own architectural design workflow, we started designing rotational surfaces, modular construction. We thought, how could we combine these to create beautiful shells? And we created a parametric workflow to quickly combine these rotational surfaces and also to then fill in these meshes. We could do all that on the fly, and we would have the rationalization later. So we were really excited. We started testing timber and looking at timber local wood and the properties of it. And then we called up Holzbau Ammann and said, we need ash wood in 8 millimeters, because that would be perfect for our design shape. And Holzbau Ammann said, we can do that for you. We can take a typical lamella and just sand it off until we have 8 millimeter, and then we can send it to you. And so this was, of course, going against our idea. Our idea was to use the real material from the sawmill and to use it directly in the structure and to maybe even reuse it. So we had to go backwards. So we asked, what is the typical profile that you get out of the sawmill? And they said, the smallest thing we can produce is 100 by 25. And then we can just split it in half one more time. That gives you 2 sections of 12 millimeter. So we actually had to go backwards and just work from that and then redesign the building for this particular section. We were using ash timber, which is really strong and very elastic. It's great. It's what's used for hammer stills and bows and arrows. And it also is in high supply at the moment because of a fungus called European dieback. So there is a sad reason why this was actually quite cheap to get. So we redesigned the structure to fulfill exactly these bending radius that we were allowed to 1.7 meter. And this is what we got, this triangular dome that should work as a grid shell. We then went back to Hui, and she wrote this optimization for this particular shape that would not only allow us to have asymptotic and geodesic planks, but also that all the angles would be exactly 60 degrees. So we have repetitive joints again. And also that all the edges would also follow these straight planks that would be geodesic. So we got the optimized mesh back, turned that into a NURBS geometry, and did the final designs. And now with this geometry, we can build the whole grid shell just using these hexagon studs as the joints. All the material we're using is flat ash timber from the sawmill, as well as flat mullions and flat sheet plastic for the polycarbonate for the facade. And all of this then went together to build the concrete, the timber grid shell. And I'm just going to show you a few more images of this project. This is how we prepared the pieces and milled them and drilled them with our templates. And then in this case, we actually prefabricated the curved beams. So we took always 2 planks, put them together, bent them in the right shape, and these curved elements were then assembled flat on the ground with an interlayer of lying planks of geodesic planks. Again, like in the first pavilion, the nice thing about this is that we can nicely assemble on plan. We did it in 3 prefabricated modules. The module in itself is now ready and bolted together and is then bent into the 3-dimensional geometry. At this point, the flat planks, the geodesic planks, are not fixed yet, right? They're sliding still, or else this would not be movable. But once it reaches the 3-dimensional shape, we then fix these geodesics, and we get this module that we could just roll out of the workshop, combine with the other modules, and finally put on prefab concrete blocks to be supported as a grid shell. And once the structure was finished, we had to add the facade, all from planar polycarbonate panels that had to be slightly tailored, though, to create this doubly curved, smooth facade surface. So this is the project we just finished last year, and this is the first time that we really have something that we think is a building product. So we're working with Holzbau Ammann now to develop this further using a Zukunftsbau funding over the next 2 years. The project was also tested for its structural performance. So we got together on a winter's day and filled 13 barrels with 200 liters of water. So 26 kilonewton on one side as an asymmetric load, just to prove that this is not anymore, an indoor pavilion. This is really a very robust structure, and we actually laser scanned at each iteration of adding load. We scanned the whole structure and compared the deformation to our computer model, which was quite accurate. And with this, we're now working also with material scientists to look at the long-term behavior of the timber when you deform it like this, and especially with the high torsion in it. And we're getting the structural approval for this as a building product. So with this, I want to close my talk, and I think I'm 2 minutes over, but that's fine. I hope I could show you a little bit of how you can use geometry, structure, and construction to create meaningful design. And if you liked it, please don't forget, apply for a position at the University in Hannover. Thank you.
Thank you very much, Eike. Thank you for this excellent presentation. Questions? No questions? Here. Felix.
Yeah, thank you for this really nice talk. I enjoyed it a lot. I have one question. In this AAG webs in the end, like the model that came out of the computer program, where you had geodesics and asymptotics always meeting in a common vertex, in a common node.
Yeah, that's
and then
right.
when you produce it, you offset the geodesics slightly. So, like, is this for practical construction reasons, or is this?
Yeah.
Yeah, where does this shift come from?
Why do we shift it? It has, thank you for the question. I always, when I'm in such a hurry, I forget the most important. So generally, whenever we do an optimization, a mesh optimization, we make it much denser than the final product. That gives us the option of having much more information for intermediate intersections and so forth. So you can see the mesh on the left, and we're actually only using every second element. So to get to this trihex, we only have to choose every second one, and then we get that. So that's pretty much the same mesh, just not picking every line. Why do we do it? It's 2 reasons. It makes the construction easier, because suddenly we don't have one joint where all 3 meet, which have to go through each other, but we can split the geodesic out, and we can actually add it later. We can just slide it through later, making it really simple to assemble. Even if one breaks, we can just replace it very easily without opening any joints. And the other, much more important reason was buckling. In the previous steel grid shells that we've built, buckling was always the biggest problem, right? Because between joints, you only had 2 millimeter thick stainless steel. At any compression, even if we added several lamellas together to create a stiffer section, it would still start buckling as the first mode of instability. Now we're using timber, and because timber can be thicker for the same bending radius, we have way less a problem of buckling. But additionally, by shifting this geodesic lamella, we are halving all the buckling length. So before we had a node distance value of 60 centimeter, now we have a geodesic lamella in the middle, now it's 30 centimeter. And actually for this kind of assembly, buckling is not an issue anymore. So under all this load test, buckling was never the case of instability, but it was more that we got the yield stress of the timber at some point. Does that answer your question? Yes. Yeah. Yeah.
Didn't you motivate like this additional introduction of geodesics to have simpler faces? Or maybe I'm confusing this now.
Yeah, I motivated it to actually also add a facade to it, right? And so the same element that we're using to brace the structure is also the mullion, the aluminium mullion that holds the facade. Thank you for the question. I realize now that I never actually explained that, but when you later put the facade on, it follows exactly the same path, just on top of the structure, holding here you see it, the developer panels in place. Yeah. So it's the same one, just an offset of it. Yeah.
Maybe one more.
Thank you.
Quick question.
Thank you very much for this very interesting presentation. It's fascinating what can be done in this geometry. And one question is, why did you cover this structure with a rigid element and not with a tensile membrane or a film?
This particular one, actually, we had this idea before, also for the first pavilion, we could just stretch membrane over it, and it's a minimal surface, right? Yes. Perfect. So there are several reasons. I think you can do either. I think if we would really stretch a membrane over it, we would have to ask ourselves the question, why did we build the grid in the first place? Because the membrane is absolutely fine with just the boundary edges. So I think there is a reason to use membranes sometimes, but we wanted to show that you can have really absolute standards. These are these polycarbonate hollow profile off-the-shelf piece that you can buy in every store, and we wanted to show that there's a very simple way of cladding this in it, like you would clad any greenhouse, and so we chose this for that reason. I think for other architectural purposes, like our architectural project, we wanted a membrane, and there we actually had a membrane that was stretched by an arch. I think you can look at both. It's not either or. Yeah.
Thank you, and congratulations. Brilliant.
Thank you.
So let's leave it with that. Thanks again, Eike, for this really nice presentation.
Thank you.
Thank you.